Okay, so today we're looking at chapter 23, electric potential. Having a little bit of an issue with my mouse. Okay, so electric potential. So what we're going to see is that this is quite a bit like potential energy, but not quite. We'll try and draw a few parallels to what we've seen already with gravity. But this concept is going to be important for us moving into the subsequent chapters on circuits and so forth. So let's take a look here. So the first thing that we want to actually take a look at is going to be electric potential energy. This can be confusing sometimes for students. We'll try to be as clear as we possibly can about it, but these two things are different, electric potential and electric potential energy. So let's try and differentiate between the two as early as possible. So electric potential will have units of volts, and electric potential energy is an energy. So what units do we use for energy, right? We use joules. So try and differentiate between these two right away. Okay, so one is measured in joules and one is measured in volts, so we know they're different. Okay, let's start with a simple picture. And the picture here is going to be something along the following lines. We have a point A, and we have a point B, like so. And we have some sort of charge here at point A, and that charge moves along some path from the point A to point B. We can give this path a name, call it C, typical name of a path. Okay, so the question that we want to ask here is that if this charge moves along the path A to B, how much work is done on the charge? Okay, so the work in moving from A to B is equal to what? So that's our starting point here. Well, first off, we know what work is from last semester. In general, we can always write down the work done on a particle in terms of a force, right? So that's going to be an integral on some path. This is why I gave the path a name, C. Some force vector field F that acts on the particle, dotted into some differential which measures length along the path. It's like dr, for example, here. And so since this might be something that you guys have forgotten, I'll go ahead and stop here for a second and let you guys ask questions about this if you guys remember this, or should I do a little bit of a review on this? So go ahead and let me know. You can use the hand emoji or write something in chat if you have a question about this. Okay, give me a thumbs up then if we should continue. Okay, it's pretty decent number of thumbs up, but not quite enough. So if you haven't given a thumbs up, please give a thumbs up if you're good to move forward here. I do see one chat here. I would like a little review. Okay, so let's go ahead and take a look at, let's go ahead and take a look at just this integral real quick and see what it's all about, just on the side here. So we're saying that work in going from A to B is some integral along a path C on some force which acts on a particle along a path. Okay. Let's take a look at a simple example here. Suppose we have a block and a force F, which is constant, acts on the block. Well, it's pretty obvious that the block is going to move in this direction if we apply this force to it, and that's the only force that's acting on the block. Okay, so our displacement will be in the positive x direction, and the force is acting in the positive x direction. So what happens over here with this integral? Well, we can rewrite this integral. Instead of integrating along some complicated path, well, we have here an x1 and over here an x2 where we end up, and x2 minus x1 is basically delta x, right? Okay, so our integral would look something like x1 to x2. We would integrate over dx instead of dr. Dx is measured in the positive x direction, which is the same direction as the force F. So here, the dot product between F and dr is simply F times dx, and F is constant here. We can pull this out of the integral. So we have the force F integral dx from x1 to x2. And then again, integrate dx, we get x, and then it's x2 minus x1, which is delta x. So F times delta x. So this is overkill for a simple problem like this. We obviously don't need an integral. We kind of already knew that the work should be force times delta x, hopefully. We can maybe take a look at this a little bit further. We could say, okay, we also remember that work is mad, right? You guys remember this? Work is mad. So we change the force here into mass times acceleration using Newton's second law. And in our case, it would look something like ma times delta x. So oftentimes you can use the work like this to calculate an acceleration if you have constant acceleration, something along those lines. The next thing to remember here, I'm going to erase this work is mad piece here. The next thing to remember is that, of course, the force and the displacement do not have to be in the same direction. So I could have a situation where we have delta x is this way, but I have a force in this direction here. Technically, delta x here is a vector, so I should have put a vector sign over that. But okay, so we have a force kind of in the opposite direction as our displacement. You could think of this as somebody pushed the box, but then after they push the box experiences some friction force, and so F here is kind of slowing the box down over time. And so if this F here is a friction force, then it goes against the motion. Then what would happen? Well, we would again have, work from We don't have to say work from A to B now. At this point, we can say work from x1 to x2, actually. So if we, again, do work from x1 to x2, what we would see is that for this dot product here, the vectors are pointing in opposite directions. But again, our force here and delta x are each, they're basically constant in this case. Nice simple example. So we pick up a minus sign, and then we have the integral again from x1 to x2, f dx. This whole thing will integrate again, and we'll just give minus f times delta x. And so work can also be something that's negative. That's the point of this second example here. So work can be positive and it can be negative, and that's going to be important for us in the following way. We can have work done on a positive charge. We can have positive work done on a positive charge, negative work done on a positive charge. We can have positive work on a negative charge, and we can have negative work on a negative charge. So it's important to understand what's going to happen in each of those cases. So if we have negative work on a negative charge, what does that mean, right? So there's what happens there when we have work. Now, real quick, there's one other super important thing that you learned last semester. It's called the work energy theorem, and I will just quickly go over that. So what is the work energy theorem? The work energy theorem, WE theorem, says the following. It says that the total amount of work done on any object is equal to its change in kinetic energy. Simple as that. That's the work energy theorem. Simple as that. How do you get that? You start with the fact that acceleration is the time derivative of the velocity. Actually, let's drop the vector signs here to keep things simple. We don't want to look at the vector version. Acceleration is the time derivative of the velocity, okay? But I can use the chain rule here in the following way. I can say dv over something times something over dt is the same as dv dt, as long as what I put here and what I put here is the same, right? So that they cancel. So what do you put there? You put dx. Put dx here and you put dx here. Okay. So all we're doing is just using the chain rule. That's it. Now this thing right here is velocity. And this dv dx, you leave it as is. Okay, so now the acceleration, we've used some chain rule magic here. We know the acceleration is also equal to v times dv dx. Okay. And now what you do is you just integrate this thing. So you can multiply both sides by f and dx. You can multiply both sides by m so that you have a force on the left side, and then multiply by dx so that you have an integral for the work. So you have ma equals v dv dx with an m. Sorry for the handwriting here. Okay, and then you slap dx on both sides, since we're doing this in one dimension. So I'm having a little bit of problem with my mouse right now. It's not giving me, like, when I click it, it's kind of like choppy for some reason. And you integrate both sides. So why did we do this? Why did we multiply by m? We multiplied by m because that turns the left side here into a force. And we integrate a force over a displacement dx, and that's the work. So that's what we were doing there on the left side. On the left side, we're making this thing look like work. And on the right side, we have this kind of weird looking expression here. But we just want to see what comes out on the right side. That's why we make the left side look like the work, and we want to see what comes out on the right side. And what we see is these dx's cancel here, and we have mv dv. mv dv integrates to 1/2 mv squared, final minus initial. Okay, so that's what it is right there. So the right side comes out to 1/2 m v final squared, v final squared minus v initial squared. So that's a difference in kinetic energies right there. So there it is. That's where it comes from. Those are some important things you have to remember about work. There is one more fact that we need, and then we're done with our review, okay? So one more fact, and that's it. So now we have that the work is this integral, okay? We have the work energy theorem, and now we need potential energy. How do we define potential energy? This is a technical thing that I think some students kind of forget, that you actually need to define the potential energy. So let's take a look here. We can leave like this integral here. I'm going to go ahead and erase this now. This is what this should look like here. The work is equal to that difference in kinetic energy there. So how do we define potential energy? So potential energy how do we define it? Well, the very first thing that you have to understand is that you cannot define potential energy unless you have a conservative force. So, defining potential energy, if F is conservative, then we say that the work is equal to, and there may be a minus sign here. Let me double check. Yes, okay, so the work in going from A to B is minus the change in potential energy. Okay. So if F is conservative, then we define this thing. We usually use the letter U, although in your last semester physics class, you used PE most likely, right? You probably use delta PE. So delta PE, because the PE stands for potential energy. It's nice and easy to remember. Standard notation though in this class is U, and we will use U in the textbook, and I'll use U as well. So just get used to that. That's standard notation from here on out. Every class after this class you take will most likely use U. Okay, so there's our definition of potential energy. What this quantity is energy based on your position. Kinetic energy here is energy based on your motion, right? It depends on velocity. But what you'll see is that potential energy always depends on position. And so that's why we need the force F to be conservative, because if the force F is conservative, what does it mean? It means that it actually means a couple things. The most technical way I could define a conservative force here is to say that the curl of the force is 0. This is a nice little expression for determining if a force is conservative. Give me a thumbs up if you know what this statement here means, the curl of f equals 0. Okay, so very few people. Okay. This operator here, first off, we usually refer to this as del or nabla. That's what this symbol is called. N-A-B-L-A. This thing here operates on vectors. It's a cross product. Okay. The actual symbol here, what it is, if you wanted to write down what it is as a vector, it looks something like this. It's a vector of operators, a vector of partial derivatives. So it's a partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. So that's what it looks like as a vector. And you just need to do a cross product of this vector of derivatives with f. Okay, so do you guys remember how to do a cross product? Not too many. Thumbs up if you know how to do a cross product. Okay, so it's really as simple as just doing a cross product, except that you just have to remember that, okay, your vector here is a vector of derivatives. So when you do your cross product, you just make sure that you take those derivatives, and it's as simple as that. So we're not trying to make anything in this class super complicated. So if you want to use this to check if a force is conservative, go ahead. There's another way that you can know if a force is conservative. And that is if the integral, and my mouse is giving me trouble, huh? Okay, so if the integral on a path C1 is the same as that integral on a path C2. Now, what does this mean? This means that this integral here does not depend on the path C1 or C2 and so forth. It doesn't depend on the path. So the integral does not depend on path. Right, so if that's the case, then f is also conservative, okay? And again, if f is conservative, then we can define this potential energy. The work done from the work done on a particle as it moves from A to B is equal to minus its change in potential energy. So simple examples of potential energy like mgh, right? mgh or mg delta y, right? The force there is the weight, mg, and then as you go up higher and higher away from the surface of Earth, you gain more and more potential energy, right? So now you know that the force mg is a conservative force, right? You probably knew that last semester. It was probably mentioned. And so you could define this potential energy, mg delta y. So notice that the potential energy depends on position here. It depends on this quantity delta y. The more delta y you have, the more potential energy you have. Okay. Any questions about that? Give me a thumbs up if we're good to move forward. Okay. There's one there's maybe one other thing we could look at here while we have things nice and simple before we move back to electrostatics. And that's the following idea. When I write down mg delta y, I assume that the potential energy is zero somewhere, right? Do you guys remember that? So I can say that the potential energy here at this line is zero, and then it goes, it becomes positive as I go up. It's positive up here. But if I were to go down, it would become negative. I'm free to make that choice, right? So maybe some of you have done some problems last semester where you didn't have zero at ground level, but maybe you had zero was up here, and down here is negative and higher is positive, right? And you were free to make that choice. You were free to choose your 0 point. And so we will do that as well. And we'll see that in some cases, we're actually forced to choose zero at a certain location. And so that's kind of interesting because we haven't seen that before. Part of the reason why we haven't seen that before is because you actually never look at gravitational potential in a first semester physics class. So if you did, then you would have already seen this forced choice, but yeah. Okay, so I'm going to go ahead and clean some space off this right side corner here. Go ahead and ask me any questions if you have any, or just give me a thumbs up if you're good to move forward. Okay, so I haven't seen any hands or any chats, so I'm going to keep going here. The next thing that we should consider for our picture here, let's just recap. We've got this point A and we've got this point B here, and there's some curve connecting those 2 points. And we've said we have this positive charge over here at the point A, and it's going to move along this path from point A to point B. Okay. And there's some sort of electrical force acting on this particle. So it might be a good idea if we draw in some electric field lines now. So let's go ahead and say, let's draw in some electric field lines. And these field lines can be as complicated as you want them to be. They don't have to be nice and simple and uniform, because what we have here is a general answer for what the work is. So they can be a little bit curvy like this. That's fine. As long as your electric field lines don't cross, right, then it's fine. Okay, so we can maybe even make them look like they're not going to cross a little bit better. So we have this charged particle moving in this electric field, which we've labeled E. And the charge here we can say is a small plus Q. And work is going to be done on this charge as it moves from point A to point B. Okay. Let's write down a little bit more here. So we can change the force on a charged particle from F to Q times E, right? So that's one thing that we can do, a little preliminary step. And so we can pull the charge out because Q does not depend on what's being integrated over inside our integral, right? Which is a displacement vector. And so for electrical work, this is our kind of our final answer. This is as far as we can take it without assuming something about E and about the path that we're on. So that's as far as we can take it there. Okay. Well, we said that if F is conservative, we said if F, there we go. If F is conservative, then that implies that the work from A to B is minus the change in potential energy. Okay. Well, in our case here, we need E to be conservative, right? Yeah, we can have F as conservative, right? But F we write as Q times E. And so if E is conservative, then F is going to be conservative, since Q is just a multiplying number, right? So this implies that if E is conservative, then we have the same thing here. We can define this potential energy. Okay. So are we good with that? Hopefully that's pretty clear here where we're going with this. Okay. Just a little bit of foreshadowing here. The reason we're kind of replacing the F with Q times E is when we take a look at this thing, we're going to divide out the Q. When we divide out the Q, that's when we're going to get electric potential rather than electric potential energy. Okay, so I'm going to clean this up now, and we'll take a look at electric potential energy for a point charge electric field. So suppose we have a point charge here. We know what its electric field is doing. Looks something like this. This is a plus Q. Actually, let's call this capital Q here. If I just have this electric charge just sitting here in space by itself, it doesn't respond to its own electric field. It doesn't exert a force on itself. So if I have this situation as drawn here, there's no work. Okay, there's no work being done on anything. This is just a charge in space somewhere. But if this charge, let's say, is some fixed charge plus Q, it's fixed at this location here, and I say, how much energy do I have to spend to move this charge in from a position really far away? Let's just call it position. Actually, let's use the same labeling as before. This is the point B, or sorry, the point A. This is the point A. And we move this charge closer, right? This charge, as we move it closer, it's going to require energy because it's a positive charge, right? It's being repelled by the other positive charge that's already there. And so that would require us to force it into that location. We'd have to apply a force, right? So we'd have to do work to do that. How much work would the electric field of the big plus Q do, though? Well, the big plus Q has an electric field pointing in this direction at that location, and it's pointing in this direction at this location, and so it would do negative work, right? The electric field of this big plus Q here would do negative work. Let's go ahead and use a different color there for the for the electric field. So the electric field is pointing in that direction there, pointing in this direction here. Okay, and so there's two questions to really ask here. The first question would be like, how much work do I have to do to move this positive charge closer to the big plus Q? That's one question, right? And then the other question is, how much work does the electric field of the big plus Q do as this, I forgot to label this guy little plus Q, as this little plus Q moves closer to the big plus Q. So how much work do I do, and how much work does the electric field do? So two questions, right? And we get the same answer in principle because we would have to apply a force equal to and opposite the force of repulsion here. So we would have to apply a force at least equal and opposite to that force. And so in principle, we could get the same answer there. But what is the form here of the electric field? This is key to doing everything here. So the simplest path we could use to connect the points A and B is a straight line. Okay, so straight line path. So C is a straight line. Okay. And the electric field magnitude is KQ over R squared. Want to add in the vector direction. It's in the R hat direction because it's a positive charge. So positive R hat there for the direction. If we had a negative charge, make sure you put negative R hat, right? Now we have the electric field. We know what our path is. Let's think a little bit about what's going to happen with the integral now. So let's go ahead and write the work in moving from A to B is equal to this integral Q times the integral along the path C of E dot dr. Now, what do we do with dr here? Well, dr is measured in this direction, right? Along increasing r. Well, our particle, let me clean that up a little. That arrow is kind of big. Our particle that we're interested in calculating the work done on is moving along this direction though. And so we have two drs here. Okay, we have two drs here. So it's important that we understand which dr we actually need to use. So this is the dr which tells us the increasing direction of r. Okay, and we have this dr here, which is the dr for our path. Okay, the two are basically related by a minus sign. The one that we want to use so that we have a nice clear picture of what's going on in our heads is not this one, but this one over here. Okay, the dr that moves from A to B. Just keep that in the back of your mind. Just always use a differential along the path which goes from your starting location to your ending location. Okay, and so that dr there goes from big R. Let me write that down as, this is R at the A location. Try and write that nicer. R at A, and then of course we have R at B over here. This is R at B. And then I'm not going to draw the line because it's going to be real messy here, but RA is this really long distance from big plus Q all the way out to the point A. Okay. So let's go ahead and go back to our integral here. Now we kind of know what's going on. dr and E are pointing against each other. And so we'll pick up a minus sign when we do this dot product here. Just to be 100% clear here, let me come back up here to dr, this little vector. This is going to have magnitude of dr, and it's going to have direction of minus r hat in this case. Minus r hat. Just to be perfectly clear as to what this vector is. For the electric field, we can plug in the k q over r squared times r hat. Then we have a dot product here between dr and minus r hat. And there's one more thing we can do. We have c in our top integral here. We have c. Well, we know what c is. It's a straight line path from RA to RB. So RA at the bottom, RB at the top. Okay. All right, dot products. R hat, dot product R hat. What do we get? R hat, dot product R hat. Right, we get 1, right? But we have a minus sign here. We gotta keep track of that minus sign. So minus Q integral RA to RB, KQ over R squared dr. Pull the K and the Q outside the integral. So minus K big Q little q integral RA to RB. We're integrating 1 over R squared dr. We all know this is a power rule integral, hopefully. So r to the minus 2, right, gives us negative r to the minus 1. So we get minus KQQ times negative 1 over r. We have to evaluate this at RB and subtract at RA. And now we kind of need some more space here. Okay, so take a look here. So this is equal to minus K big Q little q, and then we plug in, so minus 1 over RB minus negative 1 over RA. A lot of minus signs flying around here. Be careful. So we have minus KQQ times negative 1 over RB plus 1 over RA. like so. So question for you guys at this stage here, is our answer here for this final expression here, is it greater than 0? Is it going to be equal to 0? Is it going to be less than 0? Something to think about. Okay. This is our answer here though. We can clean this up a little bit. We can distribute the minus k, q, q. So we have k, big Q, little q, over RB, minus k, big Q, little q, over RA, like so. This is our answer. Okay, so I'll give you some time to copy that down and think about that question I asked. Try to make some more space here.
Professor, can I
go? Yeah.
I'm thinking it will be less than 0 because as for the work going from A to B, it's opposite to the direction of the electric field. So just like for the F delta X, since it's going like opposite direction, so it would result in a negative, meaning less than 0 rather than greater than 0. Would it work from A to B?
Okay. So remember, it does depend on who, what question you're asking, right? So remember, there are two possible questions that we could ask here. What's the work that we would have to do? And what's the work that the electric field of the big Q has to do as the charge moves in its electric field, right? So there's two questions there. So when I ask a question like this, like what is the sign of the work? It's important that you understand what the sign would be for both cases, right? So think about that. Think about what the work should be if we're the ones doing the work, and what the work would be if we're asking what's the electric field, what's the work the electric field is doing on that charge. Two different answers there, right? So mathematically, we look at this answer here, we can tell that this answer is actually going to be a positive number. How can we tell this is going to be positive? Well, RA is bigger than RB, right? RA is bigger than RB. And so what does that mean? That means that this thing that we're subtracting here, this KQQ over RA, is smaller than KQQ over RB, right? And so just as an answer here, this particular answer is going to be greater than 0. Okay? It's going to be greater than 0. And so what this means is that the work that we have to do on this charge is positive. We have to push this charge. We have to push this charge against the electrical force of repulsion here in order to bring it closer to a positive charge. Okay? So this is positive if we do work. If we push Q closer to big Q, and negative, I don't know if I have enough space to write it here, but I'll try. Negative I should put negative work done by the electric field of big Q. Okay. So any questions about that? Any questions about that example there? The next thing that we're going to do is we're going to take the limit as RA goes to infinity and see that that's where the potential should be zero. Sorry, the potential energy should be zero, right? Because you're infinitely far away. That makes sense. If you're infinitely far away, then there's zero potential energy. And so that clues us into where the electric potential here, which is coming up in a minute, should be zero. So any questions about that? Use the hand emoji or write in the chat. If not, go ahead and give a plus, or sorry, not a plus, thumbs up. Okay. Looks pretty good. Let me clean some, well, actually, we don't necessarily have to clean some space up just yet, actually. So what I just said was we can take the limit on this thing. So this is the negative change in potential energy, right? The work in going from A to B is equal to the negative of the change in potential energy. So the negative of the change in potential energy is KQQ over RB minus KQQ over RA. And so we can see from this that actually the change in potential energy is negative. Well, how can we see that? Well, delta U is equal to minus, I just moved the minus to the other side. Okay, just move the minus sign to the other side there. So the change in potential energy from of the charge here from the point A to the point B is given by this expression here. And now what we want to do is we want to take a limit as R sub A goes to infinity. What happens as R sub A goes to infinity? How should we write this here? So let's just go ahead and skip the writing out the limit and everything. I think we can all kind of see, like, if this thing goes to infinity, then this term goes to zero, right? We'll just write it like that. Actually, I'm looking at this thing and I'm thinking I may have a sign error somewhere here, because my intuition tells me that if we have a positive charge wants to go from high potential to low potential. It wants to go from high potential energy to low potential energy, kind of like how a mass wants to fall from high potential energy to low potential energy. So I think I have a sign mistake here somewhere. Did somebody notice like an extra minus sign, or maybe I forgot to put a minus sign in here somewhere? Like I dropped a minus sign? Just like raise your hand or say something in the chat if you notice here. Let me just go ahead and look back through all this. I think I missed a minus sign, and I'm just barely noticing. Okay, I double counted a minus sign here. Okay, yeah. I double counted the minus sign here. So what I should have done, was actually, if I use this idea here that dr is in the negative r hat direction, I should have integrated from r sub b to r sub a. I should have also flipped the order of integration here. I should have also flipped the order of integration here because, yeah, that's the mistake right there. So in principle here, it should have looked something like this. This step should have looked something like this. So q integral rb to r sub a, k q over r squared r hat dot product dr minus r hat, like this. Because I should be able to get the same answer. I should be able to get to the same answer if I measure dr this way. And if I measure dr this way, then my integral would be from, wait, maybe this isn't where I made the mistake, actually. Hold on, let me think about this for a second. So from RB to RA, dr and the electric field are in the same direction. And then I can just put a minus sign in front if I want to go the other way, because the answer will be related by a minus sign. So yeah, so in this case here, it would be q integral rb to ra. The reason I didn't do it this way the first time is because the way we set up the problem is to move from A to B. So I wanted to be careful and do everything from A to B. But of course, if we go from B to A, it's the same answer with a minus sign. So let's just write it down real quick. From B to A. So it would be integral from B to A of E times, so it'd be E r hat dot product dr r hat. Now the dr vector and the E vector in the same direction, so we get 1. So it would just be E dr, integral of E dr. I can just erase the r hats there. Erase the r hats. E dr. And then if I put a minus sign out in front, I can switch the order of integration for RB and RA. So let me take a look now. So here we had this expression right here. So E is going to be KQ over R squared, dr. But no, there is a minus sign here still. Oh no, so I think maybe I didn't make a sign state mistake there actually. Mm, make a sign mistake here somewhere. Okay, let me just consult the book real quick, just so I'm not sitting here using up too much of our time here. So I'm pretty sure the book does this for point charge. Somewhere in here. Okay, so it should end up with RA minus RB. Yeah, so there is a sign mistake here somewhere. Maybe something I need to look at myself later. But okay, so there's a sign mistake here somewhere. So it should look like this. It should look like this. Let me go ahead and clean this off here. This is the answer that we should get. So I want to make sure that everybody knows what the correct answer should be here. So the change in potential energy here should be equal to K, Q, big Q, little q, over R minus K, big Q, little q over R. And then you can use your intuition from last semester to figure out how it should go from here. So if I have a positive charge, it wants to go from a high potential to a low potential just naturally. So what does that mean? That means that over here at the point B is high potential energy. Over here at the point A is low potential energy. So this charge is going from low potential energy to high potential energy. So it should be gaining potential energy. So delta U should be a positive, it should be a positive number. So in that case, then it has to be R sub B minus R sub A, because R sub A is it's a bigger distance. So you're going to subtract a smaller number. So this overall is greater than 0. This overall is greater than 0 here. And see, now you can see why this answer is wrong here, that's boxed. So this answer right here is wrong because this right here, what we calculated is minus delta U. So I have to think about where I made a sign mistake here, and I'll get back to you guys on that if I think of it. But I probably have to just go through this again and just be more careful. I missed a minus sign or something. But yeah, so definitely the thing that's correct here, right here, this should be our answer, because our charge, when it's far away, it doesn't feel as strong of a repulsive force. So as we bring it closer, there's a stronger repulsive force there. So we're gaining potential energy as we come closer. And then if we were to let that charge go, its very large potential energy would be converted quickly into kinetic energy and shoot that charge away, because it's a big repulsive force. Does that make sense? Give me a thumbs up if that logic made sense there. So I apologize for this.
Explain it one more time.
This math here, but yeah, I'll say it one more time. Yeah. Okay, so the charge is positive, right? We have two positive charges. So if I bring one charge close to the other charge, it wants to move away. It's a big repulsive force, right? So because it's a big repulsive force, I'm adding potential energy as I move to the left. If I move to the left, the change in potential energy has to be bigger than 0. Because if I let that charge go, what's going to happen? It's going to shoot away, right? Repulsive force, big repulsive force. So if I bring it close, it will shoot away if I let go. So that's big potential energy, right? That's like if I have a mass and I lift it really high above the earth and then I let it go, right? What's it going to do? It's going to fall down towards earth. It's going to go from high potential energy to low potential energy. So you lift a book up on top of a building and then drop it over the building, it falls back. It goes from high potential energy to low potential energy. So same thing here. So if I bring the charge in close, it's gaining potential energy. So it should be a positive answer there. If I let it go, then it flies away towards low potential energy. Okay, so positive charge wants to go from high potential energy to low potential energy. Negative charge wants to do the opposite of that. Okay, so did that make sense? Can we get a thumbs up if that made sense there? That analogy with gravity there. Okay. All right. Okay, so all right, so let me make a new a new little thing here. We're actually, you know what? Maybe it's been about an hour actually. So maybe let's take a break right now, like a 5 minute break. That'll give me some time to actually look at what I have here and find where that sign mistake was, um, and then I can get back to you guys on that. How about that? Can we have a thumbs up? Should we take like a 5 minute break? Is that good? Okay, and then I'll figure out this issue right here real quick. I can just kind of go through it again and I'll find the mistake there. Or maybe actually I didn't make a mistake. Maybe I just forgot what I said. Maybe I said we're doing it from our perspective or we're doing it from the electric field perspective. And maybe that's where the confusion was there. But okay, let's meet back up here at 2:45. Okay, I'll put it in the chat. So meet back at 2:45 p.m. All right, see you guys in a few minutes. Okay, are we all back here? We all back? Give me a thumbs up if you're back. Okay, it didn't look like everybody was back yet, so maybe we can wait a little bit here. So I was going back through the calculation on paper here, and yeah, it looks like what we calculated here was the work that we do to move Q from A to B. So we can write that out here. Okay, Duke, yeah, we can. All right, so let me just check again. So give me a thumbs up if you're here, so we can get back on this here. Okay. All right, so I think that's pretty much everybody. Okay, so I figured out exactly what went wrong here. So let's go ahead and try not to do everything again. We'll clean it up here, and we'll talk exactly about what happened here. So try to clean this up. Let's get rid of this here for a second. Clean this up. Okay, so what we did here was, okay, there's still a little bit of clutter here. Let's get rid of some of this. Okay, RB here, RA here. We can move this. Whoa, what did I just do? Whoops. Oh my goodness, okay. I want to talk about this first integral expression that I have here. Okay, this one right here. Okay, so what happened here? Well, okay, there's a little bit of a oh, I forgot the R hat there. Okay, let's put that back in there. There's a little bit of a perspective that's going on here. Okay, so like I said, there's two possibilities here for the question that we could be asking ourselves. We could be asking ourselves, how much work is done by us? How much force do we have to apply to a charge to move it closer to another positive charge? Or we could be asking the question, how much work does the electric field do on that charge as it moves closer to the big positive charge? Okay, so two questions there, and they differ by a minus sign. So no wonder it's easy to make a sign mistake here. Okay, so what is the answer to the question, if we apply a force on a charged particle to move it closer? Let's label this big arrow here, F. If we apply that force to move that charged particle closer to the other positive charge, then how much work would we do? Okay, in that case here, then the answer would be what we got. Okay, without the, or sorry, no. It would be what we had before, actually. Wait, no, there would not be a minus sign here. Yeah. So, okay, so to answer the question, if we had applied our own force to this particle, how much work would we do on the particle? It would be given by this integral expression right here. So dr and the force that we have to apply are in the same direction. They're both toward that big positive charge there. So there would be a relative positive sign there for the dot product. So it would look something like this. We'd be going from RA to RB, and it would be KQ over R squared with a dr. Okay, this is how much work we would do. So what we ended up calculating, because we had this extra minus sign in here with our r hat, this is the amount of work done by the electric field. Okay, so since this is the amount of work done by the electric field, this is technically correct, but it's just a little bit confusing, because usually we're the ones who, usually the question that we want to ask is how much work we do on something in order to change its potential energy, right? We lift a book up and its potential energy changes. So technically this one is not wrong. It's just it's kind of, it was calculated from a weird perspective where it's the work done by the electric field. Okay, but so how would I change this? Next time I would just be careful. I would just be careful and make sure that that minus sign is not there, and we would just draw in this force right here. Okay, so so write that down in your notes so that that's clear. The most important thing that you can remember so that you don't make a sign mistake, kind of like how I did here, is to remember the following fact, okay? If a positive charge, positive Q, moves closer, rather, let's say moves against an electric field, meaning in the opposite direction of the arrows of the electric field. So if a positive charge moves against an electric field, then that means its change in potential energy is going to be positive, okay? Its change in potential energy is going to be positive. Why? Because a positive charge naturally wants to go with the electric field, not against it. So if you push that positive charge against the electric field, then its potential energy will increase. And then when it has high potential energy, if you let it go, then it will fall, in quotation marks, with the electric field, right? Kind of like how a book, if you lift it up, will fall with the gravitational field. So this right here will help you always get the right sign for what you're trying to calculate. Okay, so always think, okay, am I increasing potential energy or am I decreasing it? And you can always use the analogies with gravitation in order to get the right answer. And then if you have a negative charge, you just flip the logic, okay? So if we have a negative charge here, minus Q, if minus Q moves against an E field, then it's a decrease in potential energy. Then delta U is negative, okay? So if you remember these two facts right here, like you really only need to remember this one, the first one, and then remember that for a negative charge, it's the opposite, then you never will make a sign mistake on this, okay? So this, I know that this could have been pretty confusing here because it's like your first time you've seen it, and I kind of botched the sign here. But if you remember these facts right here, these two facts, You will never make a sign mistake when you're dealing with potential energy or electric potential. Okay, so this is like the most important thing right here. So the most important. Most important to remember. Okay, I don't have enough space there. Okay, so as long as we keep that in the back of our minds, we'll know exactly what the sign should be. Okay, any questions before we go on to the next thing? Okay, so I'm going to go ahead and clear this up now. So I'll start by just clearing the stuff that we've already gone over here. And I'll leave those comments in the bottom right there for a minute. Okay, so we know how the potential energy changes. If we bring a charge from positive infinity close to another charge, the potential energy that's stored in that charge configuration is given by K, Q, Q. Actually, let's go to a numbering system. K, Q1, Q2 over R, where, and actually we're going to call this R12. This is the distance between R1 and R2, where U equals, well, that's supposed to be a U, not a V, where U equals 0 for R tending to infinity. Okay, so we have zero potential energy when we have a charge which is infinitely far away from another charge. But as we bring that charge in close, so first off, in order to have potential energy, you have to have at least two charges. Okay, so that's the number one thing here. So if you're going to have potential energy, you have to have two charges. Okay, or a source of electric field and one charge. But if you just have one charge, or you just have an electric field, then there's no potential energy. Okay. All right, so if I have one charge that gives me some electric field, and I bring another charge from infinity where it has zero potential energy, and I bring it in close, then the potential energy for that charge configuration with two charges is given as Coulomb's constant times the product of the two charges divided by the distance between them. Okay, and notice it looks a lot like Coulomb's law, but it's not squared here. So don't square this distance between those two charges there. Okay, don't square the distance between the two charges. Okay, that's only two charges though. We can obviously have more complicated situations. Here's a positive charge. Here's another positive charge, right? So let's call this Q1. We'll call this one Q2. Well, what if we brought in, let's say like a negative charge, Q3? Well, then what happens, right? Well, the first thing that you should understand is that this Q3 has not just moved closer to Q1, it's also moved closer to Q2. So there's a potential energy here associated with Q3 and Q1 and Q3 and Q2. So the potential energy here for this system now, suppose we start with a Q1 and we bring a Q2 in close, well then it's the same as what we had before. K, Q1, Q2 over R12. R12 is just the distance between Q1 and Q2. Well, now we have to add to that potential energy. We have to add the fact now we've brought a third charge in. We brought a third charge in from infinity. And now this guy has a distance between Q1 and a distance between Q2. Call it R13 and call it R23 here. So there's two terms for this charge. So when we first have one charge and we bring in a second charge, there's one term. Then we bring in a third charge, now we add in two more terms. So three terms in total. So there's a K, Q1, Q3 over R13. And this Q3 here, you plug this in as a negative if it's negative. Okay? So if it's a negative charge, you plug in a negative. If it's a positive charge, you plug in a positive. Okay? But there's a plus K, Q1, Q3 over R13. But then also, there's a K, that's a bad looking K there. There's also a Q2, Q3 term. And so this is where bookkeeping starts to become really important. When you're looking at potential energy, you have to make sure that you account for this new charge based on all of the charges which are already there. So if we wanted to add in now a fourth charge, so these are due to the third charge. If we now wanted to add in due to a fourth charge, okay, let's say we had another big minus charge here. Oops, another big minus charge. Well, now, okay, this is our Q4, so we now have three more terms to add to the potential energy. We have an R1, a distance of R14 here. We have a distance of R34 here, and we have a distance of R24 here. So we're going to have to add in three more terms, K, Q1, Q4 over R14 plus K, Q2, Q4 over R24 and plus K, Q3, Q4 over R34. Okay, so now it's getting a little bit more complicated. So the bookkeeping is really important here. As we add in a new charge, we have to account for all of the charges that are already there. Okay, so this is where things can maybe get a little bit complicated. You have four charges, you have six terms, right? So you have to do some bookkeeping. There is a general formula here for this, but it's something that nobody really remembers. You kind of just remember the logic of how to write down each of these terms. Let me just go ahead and quote it to you straight from the book. It's a little bit of a kind of a messy expression. So, yeah, here we go. So it's a double summation. The way they write it in the book, the way that they write it in the book here is in the following sense. So U, for a collection of point charges, they write it as 1 over 4 pi epsilon naught. We're just going to use Coulomb's constant here. And then they write a single summation, but really what they mean is a double summation. So they sum terms for I less than j, q sub I, q sub j, over rij. So what does this mean? Well, first you think about what if I is 1? Okay, if I is 1, we only have one charge, right? Well, there's no potential energy if you just have one charge. You need at least two charges to have a potential energy. Okay, so apparently J, so suppose J is 1. Okay, there's only one charge, there's no potential energy. Okay, now suppose J is 2. Well, if J is 2, then I can also be 1, right? Okay, so you first plug in J equals 2. So you're going to have a 2 here, an Ri2. And then you're going to sum over I up to 1 less than J. So the meaning of this summation then is that first we look at J. So J is going to run from 1 up to some number n. And for each J, we want to sum from I up to J. Sorry, from up to J minus 1. Okay. So this is the meaning here of this summation here. Coulomb's constant is still there. And so, oh, whoops, oh no, that should be correct. So if I is 1, or rather if J is 1, then, okay, we can't sum up to J minus 1, so there's no term. If J is 2, yeah, actually, maybe it makes more sense, actually, to just get rid of this J equals 1 here. J has to be at least 2, right? So J has to be at least 2. So if we have J equals 2, then I can be 1. If we have J equals 3, then I can be 1 and 2, right? If J equals, let's say, 4, then I is going to be 1, 2, and 3. You have 3 terms there. So there's a lot of terms that build up real fast. Remember, you're summing over J and I. This formula here is not so important, though. It's really the logic that matters here. Just follow the logic here for something like this. Look at your charges. Do the distance from each new charge to each charge that was there before, and so forth. And that should get you your answer. You shouldn't need to rely on a double summation. The double summation is only important when you have like a really large number and you kind of want to write down an expression, kind of a general answer. So you really don't need the double summation. But there it is in case you need it there. Okay. All right. I think now we're ready to tackle potential, electric potential. We've gone over electric potential energy now. So what is electric potential? So I'm going to go ahead and clear some space here. Okay, and am I clear? Give me a thumbs up if I can erase this. A thumbs up if I can erase this, and we can go to electric potential now. Okay, not quite. Not quite. Okay, I think we're good. I think we're good. Okay. All right, so what is electric potential? Well, electric potential is electric, so electric potential we use delta V for that, is equal to electric potential energy, electric potential energy, per unit charge. Okay, it's electric potential energy per unit charge, like so. Okay, let me make sure I'm following the book's notation here. Okay, they use Q0 instead of Q, so we're good. Okay, so this is electric potential energy here. It's electric potential energy per unit charge. So what does that mean? Well, let's take a look at our simplest case, right? Our simplest case here that we have so far is we have two charges like so. We have a charge like this, and then we have this little charge. So this was what we called big plus Q, and this is what we called our little q here. So these two charges are the matching charges here. So little q for little q here. They were a distance apart, a distance r apart. Then the potential energy there for that charge configuration would be K, big Q, little q over R. Okay. And so what would we see for the electric potential, which is electric potential energy per unit charge? Well, we would see that for the electric potential, we'd have K Q over R, little q canceling because we divide by little q. So it's electric potential energy per unit charge. Okay, so this is what we would get for a point charge. So maybe we should subscript this. So this is like 2 point charges on this side. But over here, we don't need 2 point charges. This is just for 1 point charge. So when we're talking about electric potential, we only need 1 charge. Electric potential energy, we need at least 2. We need at least 2 charges for to have potential energy in our charge setup. But if we have 1 charge, we can talk about electric potential. Okay, so that's our formula there for the point charge, just straight away. And we always remember that for U and V, these are 0 as R tends to infinity. So that's where our 0 point is. Our 0 point is all the way at R equals, as R tends to infinity. Okay. Any questions about that? That's pretty straightforward, right? Just divide the potential energy by that little q, and you arrive at the electric potential for the point charge, kq over R. Okay. Now, we could take a look at some situations now where we have something even simpler than a point charge. Okay. And I think we should do that first before we write down an integral expression for this potential. Remember, we had an integral expression for the work, and so we had an integral expression for the potential energy. So there's also going to be an integral expression for the electric potential. But let's take a look at a nice quick example that's actually really nice. And that is the following. Recall that if we have an infinite sheet of charge, that we have a uniform electric field. Okay, so we have a uniform electric field coming off of this thing, if it's infinite. And just to remind you, that electric field has magnitude sigma over epsilon naught. And in this case, I've drawn it so that the direction is in the x hat direction. Okay. So if that's the case, if we have like this simple setup here, and we have this constant electric field, sigma over epsilon naught, let's just, for a second, we can just say the magnitude of E is E. Okay. The magnitude of the electric field is just the letter E there. And we won't even worry about the sigma over epsilon naught because we won't have to. So now suppose that we take a positive charge here. Maybe use like red. We take a positive charge here, plus Q, and we push it towards this plate. So we apply a force here. We apply a force to move this positive charge against this electric field. Think about the following scenario here. Think about the following scenario. We're on Earth and we lift a book. Right? Here's the physics textbook, right? We lift this book up, right? And it moves up here. It has it has gravitational potential energy, right? It has gravitational potential energy mg, and then let's say delta y. Could use h, but let's say delta y. Okay. It has electric potential energy of mg delta y. What's the electric potential energy equivalent of this scenario over here? Over here we have a mass which moves in a constant gravitational field, G. This guy is a constant, right? And it moves just a small displacement here, right? Delta y. Oops, displacement. So over here, it looks like we have a similar situation. We have just a charge. We have a constant electric field here. This electric field is constant. And we move from some position over here to some new position over here. And that displacement is, let's say, just a delta x displacement, right? Just a delta x displacement there. Okay. Well, this is a really simple scenario here. So let's think for a second. Let's think about the magnitude of the work done. Why am I thinking about the magnitude? Because I want to use the trick that I told you guys before to figure out what the sign is. Okay. Well, if we have a constant force like we do in this problem, the work done, the magnitude of the work done is simply going to be the force times the displacement. F times delta x. Okay, well that's going to be whatever this charge is times the magnitude of the electric field times the displacement delta x, right? So I've simply replaced the force with Q times E. My displacement delta x there is like my displacement delta y from the gravitational case. My force in the gravitational case is mg, right? My force in the electric case is QE. Very similar. Okay. I have to do work to move a positive charge against the electric field. I have to do work. I have to push on it because naturally it wants to go with the electric field. So I have to push on it. That means I do some work on this charge. I give it some potential energy. So here, the potential energy is positive. So the change in potential energy here, the change in potential energy is positive. Mouse is giving me a little bit of trouble here. Let's actually write, so the change in potential energy is Q E delta X. Why? Because this is a positive number here. If I make if delta X is positive, E is the magnitude of the electric field and Q is positive. This is a positive number. This is the correct answer. This is bigger than 0. Okay. So the change in potential energy here is positive. It's QE times delta X. If I let this thing go, it will start to lose potential energy and it will accelerate to the right. Right? It'll pick up a 1/2 AT squared type of thing going on there, constant acceleration. Okay, how about the electric potential? What is the change in the electric potential? Well, electric potential is electric potential energy divided by charge. So the change in electric potential would be the magnitude of the electric field times the displacement x. And again, the electric potential increases to the right. Sorry, to the left. To the left, against the electric field. So over here we have, if we have this, if we say this is, shoot, right, there we go. Okay. Let's call this one V2, and we'll call this one V1 over here. My mouse is giving me problems. That's why it's kind of like the lines are choppy like that. Okay, so if we call this one V1 and we call this one over here V2, then V2 is bigger than V1. The potential at V2 is bigger than the potential at V1. Okay. We could rewrite this delta V as V2 minus V1 and so forth. All right, what's the equivalent over here for last semester? It's something you never talked about. You never talked about potential. You only talked about potential energy. Okay, well, if we just follow the definition here, so we have gravitational potential energy there. Delta U is mg delta y, right? If we were to define a gravitational potential, what would we divide by? Well, the mass is playing a similar role to the charge here, and so that's what you would divide by. You would take delta U divided by m, and you would get g times delta y, okay? So the reason that I'm showing you this is because you can always think about what you already know in terms of gravity first. If you're thinking, okay, I'm not really sure what's going on here in the case where we have the charges and the electric field, and I'm not sure what the sign should be here on this, you can always think about the gravitational case to figure out what your sign should be. Okay, so for example here, if I have a mass, if I lift that mass against the gravitational field here, this is the gravitational field, it points down. If I lift my mass, I know it gains potential energy, therefore it gains potential. And so if I look at the similar case for electricity, I know if I move my positive charge against the electric field, I will gain potential energy, I will gain potential. Okay, so always think in terms of these analogies between gravitation and the electrical case. Okay, any questions about that? Give me a thumbs up if that is making sense. Okay, that's only about half of you. Is there anything somebody wants me to explain again? Okay, let's go one more round. Give me a thumbs up if we're okay to move on here. Give me a thumbs up if we're okay to move on. Okay, does anybody have a question? That still wasn't everybody. Does anybody have a question? So use the hand emoji if you have a question. Maybe some people just kind of stepped away. Okay, it doesn't look like we have any questions, so we're gonna go ahead and keep going here. Okay, I'm gonna clear everything on the screen now. Okay, clear everything on the screen. All right. Now we talked about electric potential there, just kind of as potential energy divided by charge. Okay. Let's revisit for a second this integral, which involves the work. We're going to use this to motivate an integral expression for the electric potential, which is going to be important. Okay, so we said that the work in moving from A to B along some curve C is given by the force acting on that particle or object that you're interested in that's moving, dotted with its displacement vector. Okay, we said this is minus the potential energy here. And well, we've just defined electric potential as electric potential energy divided per unit charge, right? We divide it by the charge to get the electric potential. So then that must mean that this is equal to minus, if we, before I write that, actually, let's write over here that the potential energy per unit charge is equal to electric potential. So if I rearrange this equation, delta U is equal to Q times delta V. So electric potential energy is equal to charge times electric potential. Just rearranging. So then if I come back over here, minus delta U is equal to minus Q times delta V, right? Minus Q times delta V. Okay. So carrying on from there, whoops, we can then say, okay, well, let's take this integral expression and set it equal to minus Q times delta V. Okay, so here we have our force dot with displacement vector, integrate over some curve, is equal to minus Q times delta V. But we know that the electric force is always given as the charge Q times the electric field that that charge is in, Q times E, right? And so what that allows us to do is actually cancel the Q on both sides. So we substitute into the integral expression Q times E, like so, dot dr still, is equal to minus Q times delta V. And then we can cancel Q's on both sides. And so now instead of dealing with forces and potential energy, we're dealing with electric fields and electric potential. And so before we said something about work from A to B. So let's actually include that here. So let's remind ourselves that we are indeed going from A to B here. And so when I write out this delta V expression, it has to be it has to be VB. Sorry, my mouse. VB minus VA, because right when we write a delta, that means final minus initial, right? So if we start at A and we go to B, B is the final. So final minus initial, VB minus VA, like so. Okay. So any questions about that, or thumbs up if you are good to move on? Okay, that's only about half, so I'll give some more time here. Obviously on this right side here, rather than writing it as a delta, which is VB minus VA, which is that's pretty much the way that you most often see it, because we're going to be dealing with delta V very often. But of course you could equivalently write this instead of minus delta V. You could just write this as VA minus VB as well. That's perfectly fine to write it that way. But because we like to put things in terms of deltas, that's why we're kind of seeing these extra minus signs. Like for example, all the way up here with the potential energy, right? And in this expression here, that extra minus sign comes from the fact that we're writing delta. That's basically where it's coming from. We got to put the minus sign in there because delta is final minus initial. Okay, so let's go ahead and move forward now. I'm going to go ahead and just delete kind of this top part, and then I'll move this up to the top. Didn't grab everything there. There we go. Okay. And now the next thing to understand here is that when we're dealing with electrostatics, let's write this actually because this is kind of important. Let me see if I can maybe maybe this will be easier since my mouse is giving me trouble. When we're dealing with electrostatics, E is conservative. Okay, is there a way that we can prove that E is conservative? Well, we can use the fact that, oh, whoops, I want to draw now. There we go. Okay. We can use the fact that if the curl of something is 0, then that something is conservative. Actually, earlier I said if the curl of f equals 0, then f is conservative. That's technically true, okay, but it's actually an if and only if statement. So it goes both ways. So if the curl is 0, then it's conservative. And if it's conservative, the curl is also 0. So it's an if and only if statement. So E is conservative. Ran out of space there. So the curl of E equals 0. How are we going to show that? Well, we can start with a point charge. So E for a point charge we know is KQ over R squared, and it's in the R hat direction, right? Okay, well, wait a minute. Are we just going to show that the electric field for a point charge is conservative, or is it conservative for all electrostatic electric fields where we have static charges? Well, the truth is that everything we've done up until this point, all of the more complicated electric fields that we've seen, are built based on this point charge, right? So we write dE as, integral of k dq over r squared, r hat. And so all of the more complicated electric fields are essentially a summation of electric fields due to point charges. And so actually, yeah, we can show that the point charge electric field is conservative, and that shows that all electric fields in electrostatics are conservative. Now, does that mean if we're doing electrodynamics that all electric fields will be conservative? No, in that case, we would need to show it for that case, right? But in the case of electrostatics, it is as simple as showing a point charge is conservative. That is good enough to show all electrostatic fields are conservative. For this exact reason right here. Any electric field that is electrostatic, meaning that there are no moving charges. That's what electrostatic means, right? Is that all the charges are in place. That's where they're going to be forever. So everything is static, nothing is moving. We don't have any motion of charges. If we have motion of charges, things get slightly more complicated. And we will look at some cases like that eventually. So any electric field in electrostatics can be written down as in these terms here. So as a summation, excuse me, I should have put an integral sign over dE as well. As a summation of contributions of point charges. So you sum up all the contributions of each individual point charge. And of course, we live in the real world, right? We live in the real world where there is no such thing as an infinite number of charges. And so our integrals and our summations in principle are finite. And so they are not divergent. As long as they're not divergent, which is the case in the real world, even though mathematically sometimes we assume, right, infinite summation becomes an integral, right? We live in the real world, and so everything is finite, and therefore we can go ahead and show that a point charge, if it's conservative, then all electrostatic fields are also conservative. Okay, so let's do that now. The first thing that we need to understand is what this r hat vector is. And r hat in spherical polar coordinates, we're going to have to figure it out here. So let's go ahead and figure it out real quick. So if this is my origin, this is my x-axis, my y-axis, and my z-axis. Here's a random vector which points in the r hat direction. This vector projects down into the xy plane as follows. This angle here, we'll call it theta. This angle here, we'll call it phi. And the magnitude of this vector here is r. Of course, we're going to set r equals 1 for r hat, which is the unit vector. Okay, so if r here is this vector and theta is measured from the z-axis, then the z component, r hat sub z, is equal to simply the cosine of theta times z hat. Right? Because the cosine of theta there gives us the component along this direction. And if r is going to be 1 for a unit vector, normally it would be r times cosine, but r is 1. So for the unit vector, the z component is cosine theta. Okay, good. We've got one component. Remember why we're doing this. So we're doing this because we want to calculate this here, the curl of E. And it all depends on this unit vector here. What is this unit vector? And we figure out what that unit vector is, and then we can do the curl. Okay, that's nice. Now this component here is r sine theta, which is the same as this component here, r sine theta. Same component there. But then I have a triangle there with that and this right here, right? So here's a right angle for us in the xy plane. So we have, not only do we have this hypotenuse here, we have now this side and this side. Okay, and so the angle phi here helps us out in this case. So for the x component, r hat sub x is going to be cosine of phi times r sine theta. Well, r sine theta, r is just 1 for a unit vector, so it's sine theta cosine phi. And that's in the x hat direction. Similarly for y, so r hat y is going to be r sine theta times sine of phi. So r is 1, so it's sine theta sine phi. And that's the y hat direction there. Okay, so there you go. There's your spherical polar radial unit vector. So spherical polar coordinates there. That's your rx, rz, and ry components. So r hat over here is sine theta cosine phi, comma sine theta sine phi, comma cosine theta. So that's how you would express that vector in Cartesian coordinates. Gonna need some more space here. This is what I want to keep here. This r hat vector. Okay. We have the r hat vector. We know what E is. So E is KQ over R squared, R hat. What is R? Well, R is the square root of x squared plus y squared plus z squared, right? R is always written as x squared plus y squared plus z squared in 3 dimensions. That's the Pythagorean theorem there, right? For 3 dimensions. X component squared plus y component squared plus z component squared. You can see that just from here. Here's x, here's y, and here's z. So this hypotenuse here is x squared plus y squared, square root. Well, square this one to get x squared plus y squared, and then square this one here and add it, z squared, and that's going to get you this r squared here. When you take the square root, you get r. Okay, so it's a matter of looking at the triangles there. All right, and so we should really express E in the following way. So K, Q over square root of x squared plus y squared plus z squared times r hat. Now, we can always, and actually I should have done this instead, but we can rewrite r hat again here, actually. Another way of expressing r hat, actually, I don't know why I didn't think of this right away. I kind of just went straight to spherical polar coordinates because I was thinking in terms of spherical polar coordinates for r hat. But r hat as a unit vector can be written as x over r. My mouse is giving me trouble here again. So x over r, x hat, plus y over r, y hat, plus z over r z hat. Let's see how we can do that real quick. Let's see how we can change r hat into this expression here. Well, we come back over here to our diagram. Okay, come back over here to our diagram. And we see obviously that this component of that vector is the x component, which is just x. This component here is the y component, which is just y. And then this component here is the z component, which is just z. And so if r is the square root of x squared plus y squared plus z squared, then we also can write the unit vector r hat as its x component, which is x, divided by its magnitude, which is square root of x squared plus y squared plus z squared. Same thing for y. We can write its y component as y divided by its total magnitude, which is square root of x squared plus y squared plus z squared, and so forth. So this r down here is the total magnitude of that vector. We can just write it as x divided by r for the x component, y divided by r for the y component, z divided by r for the z component, and that's the same as r hat. So we can also write this vector as x over r, x hat, plus y over r, y hat. And you can definitely check for yourself that this is indeed a unit vector here because we've divided by r. So if I compute the dot product of this vector with itself, I will end up with x squared plus y squared plus z squared divided by r squared. Well, that's the same thing, so we get 1. Okay. So let's go ahead and pull out this factor of r here and combine it with this factor of r. Let's go ahead and use a different color. We have r's here on all the terms. We can pull it out and combine it with this factor here. And so what we end up with is kq divided by x squared plus y squared plus z squared, x hat plus, x hat plus y hat plus z hat. Okay, and now we've finally got this thing in a form where we can calculate the curl in terms of the cross product here, this del operator with the electric field, and set it to, and see if it equals 0. Not set it to 0, but see if it equals 0. Okay. All right, so let's just chug along here. In order to do a cross product, the method that I use, I write out a matrix. We don't have to use I hat, j hat, and k hat. Actually, let's use x hat, y hat, and z hat, because that's what we've been using in this class mostly. And then we write this vector here in the second row, and we write this vector here in the third row. This top row is always the same. So we have d by dx, we have d by dy, and we have d by dz, right? And then for the electric field, we have the x component, we have the y component, and we have the z component. Okay, but let's fill in each of those components now. Okay, so for the x component is going to be kqx over x squared plus y squared plus z squared. The y component is going to be kqy over x squared plus y squared plus z squared. And finally, the z component is kqz over x squared plus y squared plus z squared. Okay. And now we go about the process of computing the determinant of this matrix, and that gives us the answer for our cross product here. The cross product of the del operator with the electric field, otherwise known as the curl of the electric field. Okay, and just a heads up, the answer is going to be 0, otherwise we wouldn't be going through this. But we need to get the machinery down here. So what do we do now at this point? Well, what we do is we write, what I like to do is I draw a line through the first column like so, and the top column. And my lines intersect at x hat, so I write down x hat, and then I open up some parentheses. And I calculate the 2 by 2 determinant of the matrix that's not crossed out. And so how do you calculate a 2 by 2 determinant of a matrix? Well, it's the top left times the bottom right minus the top right times the bottom left. In this case, it's not really multiplication. It's the derivative of the bottom right minus the derivative of the bottom left. Okay. And what we see here is we have a y derivative on something which has a y squared in the denominator. And so what we get for the derivative there is k q z over x squared plus y squared. Excuse me. Oops. Skipping a little step here. KQZ, let me not skip the step. So we have to take a derivative of something which is basically 1 over y squared. The derivative of something which is 1 over y squared is going to be 1 over y cubed, right? And then multiply by a minus 2. So minus 2, and then also the chain rule as well. And so we get minus 2y. Derivative of y squared is 2y, right, in the denominator, so a minus sign. Hopefully that was making sense. You guys know how to take the derivative. It's 1 over y squared, basically. So I follow your intuition on that. I think I might have explained that kind of poorly. So minus 2y here over x squared plus y squared plus z squared, but now this quantity is raised to the 3 halves. Yeah, derivative of like y squared plus some constant here. So derivative of this with respect to y, you get 2y. You're going to get, this is basically to the minus 1. So you get this, and then the whole thing on the bottom gets squared. Oh yeah, okay, so not 3 halves, it's just squared. Let me know if I make a mistake. You see that I make a mistake. Okay, so we have this. Now we need to subtract from this term here. So the idea is we go like this. So here's another line you can draw to help you remember. You go like this. You draw kind of like an alpha symbol. So we got the first term. Now we need to do minus the z derivative of this guy now. So it looks exactly the same. Once you do it one time, it looks exactly the same because there's no z up here anymore. Now it's a y up here. So we do the z derivative now. So it's k, q, y, and it's going to be times minus 2z over the same kind of factor here, x squared plus y squared plus z squared, and then the whole quantity here is going to be squared. Okay. And that is just the x hat component there of this cross product of the curl. Okay. Now we have to come back over here to our matrix. And we just went along x hat now. Now we have to actually change. We have to go along y hat now. And now every time you change from one to the next, you always alternate signs. It's just a rule that you have to remember for doing a cross product. So it's plus, then it's minus, then it's plus. So now it's minus y hat. It's minus y hat times, now we have to do the following. So let me use red here. We go along this side now. So it's the x derivative of kqz over x squared plus y squared plus z squared. So x derivative is kqz. It's going to be times negative 2x, and it's going to be over x squared plus y squared plus z squared, quantity squared there. And then it's going to be minus the z derivative of this term over here in the bottom left. The z derivative of the bottom left is kqx times minus 2z over x squared plus y squared plus z squared, quantity squared. And then finally, I think you guys all see what's going on here, so I'm just going to kind of try and speed up a little bit because it is kind of tedious. And okay, for the last term here, we go along the z hat. Go along the z hat like so. And now z hat has this plus sign above it. Remember, we have to alternate signs, so positive minus positive plus z hat. And now we have this. So x derivative of kqy over this factor here. So it's going to be x derivative, so minus 2x, x squared plus y squared plus z squared. And then that quantity gets squared. And then minus y derivative on kqx. So kqx, y derivative, so it's going to have that minus 2y. It's going to be over x squared plus y squared plus z squared, quantity squared. That doesn't look like a plus sign, so let me fix it. And close off the parentheses. All right, what have we just done here? What have we just done here? What was the question we were trying to ask and answer, right? We're trying to figure out if the curl of the electric field for electrostatics is 0. If the curl of the electric field is always 0, then that tells us that E is conservative. And that tells us that we can always define a potential energy. Always define a potential energy. And more specifically, always define an electrical potential energy, which allows us then to define the potential. Okay. It allows us to define an electric potential. Once we can define an electric potential energy, we can define an electric potential. I think you guys can all see that the answer here is 0. Let's take a closer look, just to be 100% clear here. We have a minus 2 kq z times y minus, again, kq and then y minus 2 times z. So this term is negative, this term is positive. They both have a y and a z in the numerator. The denominators are the same. This term is 0. How about this term? Z and an x. Z and an x. Minus sign and a minus sign cancel. This term is negative. This term is positive. These guys are 0. Last term, y and an x and a y. Minus signs cancel. This term is positive. This term is negative. It's 0. Okay? It's 0. So, the electric field in electrostatics is conservative. So we've just proven that. We've proven that in general for electrostatics. We have not proven that in general for electricity and magnetism as a whole, right? We haven't proven that in general for all of electricity and magnetism. And in fact, it's technically not true in general. It's true for electrostatics, though. Okay. Once we can define a potential and we know that the electric field is conservative, then we can make a statement which is very similar to conservation of energy. Okay. All right. Let's do that now. I'd like to erase everything that we have here on this sheet. So give me a thumbs up if you're okay with that. Okay, about half, so we'll give it a little bit more time there. I'll also, if you have a question, sorry, I didn't mention, if you have a question, feel free to ask now. So if any of that was unclear. This method of calculating a cross product is not the only method. Okay, so if you have another method of calculating a cross product, like for example, one thing that people do is they write down the next row here, and then they write down the k, q, blah, 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 and then they write down the y hat row again, and so they just go diagonally across everything, and then they go diagonally back the other way. That is also valid. You can do it that way. I think what you'll eventually understand, though, is that those are just tricks that students use early in their career, and literally everyone just does it this way forever. Like everybody does it this way at every level above like an introductory course where you first see vectors. So it is kind of important that you learn it this way. Okay, so nobody's really said anything in the chat or asked a question. So I'm going to assume that you guys are pretty good on this. So let's go ahead and clear this up. All right, so now that we've shown that the electric field is conservative, I mentioned that there was this property. So if the curl of a vector field is 0, then it means if you were to integrate that vector field along some path, C1, then your answer, provided your endpoints were the same, would be the same as if you integrated it over a second path, C2, where C1 and C2 have the same endpoints. In other words, that this integral here does not depend on the path. I can pick any path that I want. As long as I go from point A to point B, I can take any path that I want through this electric field with my charged particle, for example, and I get an answer which is the same no matter what path I choose. So that's a very strict requirement on a path integral, right? If you're doing a path integral, in general, the answer is going to be wildly different if you take one path versus another path, right? So in general, this is not true, but in the case of a conservative vector field, it doesn't depend on the path. So our path integral does not depend on path. That means that I'm free to choose. Here we go with this concept of freedom of choice again, right? From Gauss's law. We're free to choose whatever path we want to choose. So we want to choose the easiest path we could possibly think of. And we've already seen a couple examples of me choosing an easy path, okay? So for example, just to relate things to gravity, we have the book example. Here's our book. The gravitational field is pointing down like this. I could have said, let me move this book in this direction and then move it up in a zigzag path like so, and then finally end up at this point up here, which is a distance delta y, that's the y component of the displacement there, above its starting location. This is the point B, and this is the point A here. And I would still end up, if the mass of this book is m, I would still end up with an amount of potential energy, mg times delta y. But I took this crazy path to get from the point A to the point B, but I still have the same amount of potential energy as if I just went directly from A to B like so, or if I went up and then went over, right? Because moving horizontally in this horizontal direction doesn't change the potential energy, right? If I move horizontally in the gravitational field, I don't gain or lose any potential energy. And so everything that we've done so far is the same for gravity. You just have to go and look at the example, the gravitational example, to kind of draw the analogy. Just to give you a sense of closure here, the vector g can be written as, something like 9.8 meters per second squared times negative z hat, right, as a vector. So essentially g is a constant vector. So if I take derivatives of g, I get 0. So the curl of g is obviously 0, right? Because I have to take derivatives to do the curl. If I take derivatives of a constant, I get 0. So every component here will give me 0, just like the other case, right? So g is also conservative. And if you remember the gravitational force from Newton's law of gravity, it's the same again. It's like minus g m1 m2 over r squared, and there's an r hat in there, right? Again, so if we take the curl of this thing, it's exactly the same. We're going to get 0 again. So the gravitational field is also conservative for Newton's law of gravity. It's not true for Einstein's theory of gravity, the general relativity, but it is true for Newton. Okay. All right. So we've fully drawn out the analogy here for gravity. I think we know what's going on. Now, what this means, the fact that it does not depend on C1 or C2, means that finally we can write down something we've been headed towards here for a while. And I need a little bit of space, so I'm going to erase this bit over here. The thing that we've been working towards here is the following. So since E is conservative for electrostatics, we can write, well, first off, remember what we had before. So minus delta V was equal to some integral on some path, E dot dr, right? Just check your notes again. This is what we had. Let me move the minus sign. Move the minus sign to the other side. So we have delta v is equal to minus integral on some curve of E dot dr. Okay. And then I claim now that since the path does not matter for this path integral, the path doesn't matter. The only thing that matters is the endpoints of the path. If I make the endpoint the same, the two endpoints, if I make them the same point, in other words, I start and I finish at the same point, then what would I have? Instead of VB minus VA, right, I would have VA minus VA if I make the endpoints the same. Well, then I would have 0, right? Okay, so let's write that down a little bit more concretely. That's where we're going here with this. So if I were to close the path in the same way, this closed symbol, this circle means closed, in the same way as Gauss's law, I will always have 0 on the left-hand side of this expression. This applies for electrostatics only. Okay, so we have this path integral expression for potential differences. If I close my path, my answer is 0. So what does that mean? Let's take a look at what that means here. I'm trying to make some space here, but mouse is giving me trouble. Okay. All right, so let's see, what does that mean here? Well, every piece of a path, suppose we have a path that looks like this, okay? And I end up here at the point A. Actually, you know what? Let's not even use A. Let's use a labeling like x0 here. All along this path, I could start making some labels like x1. Here's x2. Here's x3, and so forth. Here's x4, and then finally x5 here, and then x5 goes back to x0. All along this path, we know that the electric field, if we're doing electrostatics, which is what we're looking at here, that my integral over the electric field, my path integral, is going to be 0 from this right here. Okay? Because the electric field is conservative, the only thing that matters is the starting point and the ending point. And so if I have a delta V here, if I compute delta V for a closed path, I get 0, because I'm going to end up doing VA minus VA again. But I could break this thing down. I could say 0 is equal to minus the closed path integral on the path C, and C is this path here. Let's suppose we go around the path counterclockwise, times whatever of the electric field, whatever the electric field is there, doesn't matter as long as it's electrostatics. As long as we're doing electrostatics, there's no moving charges. We just have a field that doesn't change there. Then we know the answer is 0. But we can break the path down into many paths. This can be a C1. This can be a C2. This can be a C3. This can be a C4. This can be a C5, right? And this can be a C6. And so let me break it down. So now we'll say integral, no longer a closed integral. We're breaking it down into individual paths now. E dot dr C1 plus, or rather minus integral C2 E dot dr, and so forth, all the way out to minus integral C6 E dot dr. Well, what's the point of doing this? Well, each of these individual path integrals corresponds to its own delta V. It's the change in potential between x0 and x1. So we call this one delta V1. We call this one delta V2. We call this one delta V6, right? And so if I go around this closed path, each new location I end up at, there's a potential difference associated with that path. And so I continue to move along this path and I gain some potential. I lose some potential. I gain some potential. I gain some potential. I gain some potential. And then I lose a lot of potential. And eventually, as I go around that path, I end up at zero, a net change of zero. And so you might be thinking to yourself now, okay, so wait a minute, we have this for the potential, right? Okay, potential energy is Q times potential like so. And so this is a statement of conservation of energy here. So this is a statement of conservation of energy for electrostatics. Okay, and so what we've just shown is that energy is conserved here for a test charge. This guy right here is a test charge, okay? So this is a test charge. This, maybe we should call it Q0. Energy is conserved for a test charge along closed paths. Okay? So because the potential will sum to zero around a closed path, then that means this must be related to energy, because we have this direct relationship between the potential energy and the electric potential. Okay. And so what we've really shown is conservation of energy in an electrostatic situation here. Now let's phrase it in terms of the electric potential. So now let's phrase it in terms of the electric potential. We oftentimes refer to electric potentials as voltages. And so you can see on the left-hand side here, up to a minus sign, we have a summation of potential differences. Now for my summation here, I've said the sum of these potential differences, electric potential difference here, delta V sub I, we want to sum over all of them, given the index I, in a closed loop. We often use this, this language of closed loop instead of closed path. They really mean the same thing though, loop, path, right? A path could be something that's not closed, but usually we say like closed loop. If we ever say sum the voltages in the loop is automatically assumed to be closed whenever we use that word loop, okay? So keep that in mind. So summation of all voltage increases or voltage decreases, the sum of all of them will always give us zero, okay? But now something interesting happens. This statement here is always true for electrostatics, meaning when we have no moving charges, this statement is always true. However, this statement is not always true when we do not have electrostatics. If we have moving charges, we also have magnetic fields, which we haven't really gotten to yet, and it's not coming for several chapters. But this statement here of this thing being equal to zero, it will no longer be equal to zero when we have magnetic fields involved. And so in general, this statement is only true for electrostatics. However, this statement here, if we assume that we have potential differences due to magnetic fields, this statement is always true, regardless of whether this is electrostatics or not. This could be true in general. Okay, so this is true in general if we account for delta V due to magnetic fields. Okay, and that is one of those profound results there where it's that one, it's like conservation of energy, right? So you have to know that, right? Super important. So this is called Kirchhoff's law, or it's Kirchhoff's voltage law is really what it's called. Kirchhoff has, I believe, 2 H's and 2 F's. Kirchhoff's voltage law, or KVL for short, KVL. And we're going to use Kirchhoff's voltage law a lot more when we get into the chapter on DC circuits. We're not going to use it so much now, but it's just such a profound result to present once we've sorted out this guy right here. Once we figure that out to present Kirchhoff's law, it's very nice. Okay, so we have Kirchhoff's voltage law now. It's a statement of conservation of energy. Any questions about that? Did that make sense? Did the logic there make sense? Feel free to ask questions. Okay, so I'm not getting any questions. So I'm going to assume that we're okay here. Okay, so what else do we have left to cover in this chapter, actually? So probably energy stored in a capacitor, right? Oh, equipotential surfaces. Yeah, okay. Okay, actually, okay, so for this book, that's right. So they don't do that until the next chapter, it seems. Yeah, okay, chapter 24. So we won't do that. Let's talk about equipotential surfaces now. So what is an equipotential surface? It's kind of like what it sounds like. Equi meaning equal, and potential, right? Equipotential, so equal potential. I'm going to go ahead and clear this. Give me a thumbs up if you're done writing this down and you're good. I can clear this. Okay. There's still some people who haven't given a thumbs up yet, so maybe maybe you guys need another minute. Thumbs up if you haven't given one already. Can you give me a thumbs up? Maybe they stepped away for a second. Ask a question if you have a question. Okay, I'm gonna go ahead and clear now. Okay, so equipotential surfaces. Take a look at a point charge. Simplest case, right? Electric field lines are doing stuff like this. They're radially outward. And of course, this is a three-dimensional diagram, right? So there's field lines coming out of your screen and field lines going in your screen. behind that charge as well, right? Well, electric field for this guy is kq over r squared r hat. Well, the potential is kq over r. It's a scalar. This is a scalar. This is a vector, right? And so we can see that the potential depends on r, and it's 0 as r goes to infinity. And so since the potential depends on r, we have spherical symmetry, right? We would expect that. We would expect spherical symmetry because we have a spherically symmetric electric field, right? And so there are surfaces of constant radius around this charge which all have the same potential. Okay, so this is a sphere of radius r. Sphere of radius r. And the electric potential is the same everywhere on the sphere. So V equals constant on this sphere. So whenever the potential is constant on a sphere, we call that an equipotential surface. Equipotential surface. Okay. What it means is that everywhere on that surface, as long as you stay on that surface, your potential doesn't change. Well, what does that mean from perspective of, let's say, doing work? Well, if I take a charge and I move it around on an equipotential surface, we know that the work done on the charge, to move it from A to B is equal to minus Q times delta V. And so if we're on an equipotential surface, no work is required to move that charge around. So if I had another negative charge, let's say, on this surface and I moved it, that doesn't look very good. And I moved it somewhere else on that surface, then it requires no work from me. That charge will naturally move around freely on that equipotential surface. So if that charge had some velocity, it would just move around on that surface with no work being done. Okay, so that's what an equipotential surface is. They are surfaces in which the potential is constant. Not zero, although if a surface has potential 0, then that is also an equipotential surface. But you do not look for where the potential is 0 to find equipotential surfaces, okay? Equipotential surfaces are where the electric potential is constant on that surface. So it doesn't have to be 0. All right. Another interesting fact here is that there are an infinite number of equipotential surfaces here. For example, on this point charge, all of these spheres here that go around this point charge are equipotential surfaces, right? I could draw an infinite number of those spheres all around that charge, centered at that charge. As long as the charge is in the center of those spheres, those would be the equipotential surfaces. And for each one of these surfaces, we can say, okay, the potential on this surface, let's call it V1. It's constant everywhere, right? So we can label the surfaces based on the value of their potential. So for example, 1 volt. You know, the dark red here is a 1 volt equipotential surface. The blue here is a 2-volt 2-volt equipotential surface, and so forth. Okay. Now, the nice thing about equipotential surfaces is that the electric field has to be normal to the surface. Okay? The electric field has to be normal to the surface. So let's see that here in our point charge example. Well, our surfaces here define spheres of constant radius r. And we know that normal vectors to the surface of a sphere are in the r hat direction. So there we go. It's already true for the point charge, right? The point charge r hat is a vector which is perpendicular to the sphere here. If we draw a little patch, then we can write down the normal vector there as r hat, okay? The unit normal. And so we already have that. Okay, well, that's nice. Well, let's take a look at that integral expression that we had before. Oh, whoops. Take a look at that integral expression we had before and ask the question, is it possible to invert that expression? So I have delta V is equal to minus a path integral on the electric field. Well, what if I want to know what the electric field is relative to the potential? Like, suppose I know what the potential is. I know how the potential is changing, right? For example, here we have a function of r. The potential is a function of r. And so what if I know how the potential is changing? How do I get the electric field? Well, in that case, what you do is to invert a path integral expression like this, you take the gradient. You take the gradient of both sides. Okay, so what does that mean? Well, first let's write this delta V as V of R. Sorry, my mouse there. V of R minus some constant. We'll call it V VA, or V at some point P. Okay, this is just a constant, so that this part is just constant. In the case of a point charge, we would just make Vp the value of the potential at infinity, which is 0. Okay. So equals this integral here. What we do is we take the gradient on both sides. And taking the gradient on both sides undoes the path integral. I really wish my mouse would work. Maybe I should just get a new one. Okay, so the gradient here is, again, this vector operator of derivatives, this del operator, or nabla as it's sometimes called. It's the vector of derivatives, the vector of partial derivatives. Okay, so again, to remind you, it has components d by dx, d by dy, and d by dz. And hopefully you guys are far enough along in your calculus classes that you've kind of seen this guy already, but I doubt it. But hopefully you've already seen partial derivatives, right? We kind of already used them in that curl example. Partial derivatives only act on the variable in the denominator, right? So partial with respect to x only acts on x, even if you have x, y, and z in your expression, right? There's a nice little, there's a nice version of the del operator in radial coordinates, spherical polar coordinates. I didn't mention it before because it's pretty complicated looking, but if your function here only depends on r, then the gradient is simply a derivative with respect to r. Okay, simply a derivative with respect to r. What does this equal? Well, the gradient of the potential will be equal to minus the electric field. And so we often, because like I said, this gradient operator will undo this path integral here. And so we can rearrange this so that it's minus the gradient of that potential, minus the gradient of that potential. Oh my goodness, okay. Minus the gradient is equal to the electric field, okay? And this is a really nice way of getting the electric field. And because we're using this operator, the gradient, the del operator, to take the gradient of the potential, this guarantees that the electric field is always normal to the direction of the potential, okay? So now that we have this expression here, notice some of the important things here. The first important thing is the minus sign. The gradient operator is basically derivatives. Okay, minus the derivative of something is minus the change of that thing, right? And so what this says is that the direction of the electric field is opposite to the increase in electric potential difference, okay? So what that means is that V2 here is lower than V1. V1 is bigger than V2, okay? V1 is bigger than V2, and so V is increasing in this direction towards the charge, and so the electric field is in the opposite direction of that. So the electric field for a positive charge points away from the positive charge, and the electric potential increases as you move closer to the positive charge. Now for a negative charge, just flip the logic. So for a negative charge, say we have a negative charge here in red, the electric potential V1 is now smaller than V2, and so the electric field is in this direction. So V2 is bigger than V1 for a negative charge here. If you're further away from a negative charge, you're at a higher potential with respect to that charge. Okay, so that's how it works there. Still, for a negative charge, if you look at the potential at infinity, it's still zero. Okay, and so that works because as you get closer to the negative charge, your potential gets more and more negative. Okay. All right, so that's the idea there. So the electric field here points in this direction because V2, this is the direction of increasing voltage. Okay, so from V1 to V2 is an increase in voltage, and so the electric field goes against that increase in voltage or increase in potential. Okay, so there you go. How to prove this here, just to let you know, so I'm not leaving you, out on your own to prove this. It's actually not too difficult to prove this. What I recommend is taking the gradient on both sides, rewrite dr in Cartesian coordinates, write the vector dr as the vector. See, dr is not a unit vector. So you can write dr as dx, dy, and dz. So do that, and then write the electric field as ex, ey, and ez. And then when you apply the gradient to this integral, you can switch the integration and the differentiation, switch the order of integration and differentiation. You can do that whenever your integral converges, and this integral in general will converge. It will always converge, provided that you're not, for example, integrating from 0 to some value, right? If you're integrating at 0, well, then your electric field is infinity. So as long as you avoid r equals 0, you can switch the order of differentiation and integration. And then I think you guys can see that this vector operator here has x, y, and z derivatives, and they will cancel with the x, y, and z. They will cancel with the x, y, and z differentials here, and ultimately you'll have an expression which is the integral of dE. And if you integrate dE, you get E. So there's your proof. That's your outline of your proof. So there's your challenge. That's the challenge for you guys. Prove that if you take the gradient on both sides that you get this expression here. Okay. So I leave that for you guys to go through the motions of proving there. Any questions now? Do we all understand if the potential is increasing in one direction, that means the electric field is pointing in the opposite direction? So go ahead, ask any questions if you have any. Okay, so now I actually I haven't really been able to kind of engage you guys all that much, so I want to try and do that now. If we have, like before, this infinite sheet, okay, with, let's say, positive charge here. Well, we know the direction of the electric field is in this direction, right? Okay, so let me select this line here. Really, this is a plane. Select this plane. I claim that this plane here is an equipotential surface. I'll let you think about why this is an equipotential surface. That's not related to the question I want to ask you guys. Okay. I want to ask you guys, what is the direction of increasing potential? Does the potential increase this way or this way? So this plane is at a potential, let's call it just V for potential here. So it's at a potential V. What is the direction of increasing potential difference? So if I move left, if I move this way, is V right? Or sorry, this is the left side. I'm crazy. Is VL greater than V? Or if I move this way, is VR greater than V? Question for you guys, okay? So think about that. Give you like 30 seconds to kind of think through the thought process on that. And you can just go ahead and write it in chat if you've come up with an answer for that. Or you can just speak up. That's okay too.
Can you repeat the question again?
Yeah, the question is right here. So which direction does the potential difference increase? So is the voltage to the left of this plane bigger, or is the voltage to the right of this plane bigger? Given that the electric field is in this direction here. So this is the electric field. This surface here is not a charged surface. This is a fictitious surface. It doesn't exist. I've just drawn this surface here. This is an equipotential surface. It has no charge on it. So I'm starting to see some chat now. Okay, we've got about 5 answers here. We have like 20 people here. So let's get some more answers if we can here. What's the direction of increasing potential difference or increasing voltage, if you want to think of it that way? That's actually a nice way. And as we progress through this week, you will hear me refer to V as voltage because it's a much more natural way to call it. just call it voltage because it's the letter V, and saying potential difference, like electric potential, and also electric potential energy, right? It can get a little bit confusing. So I tend to just refer to V as the voltage. We've had a couple more. Okay, so good. That's a good number of of lefts there. Left is the correct answer. Left is the correct answer here. Let's understand why. Let's explain that again real quick. The electric field is in this direction. And we look at our formula here, this one down here in the bottom right corner that I'm circling in blue, and we see that the voltage change, the derivatives there of the voltage, the gradient of the voltage, has a minus sign in front of it. What that means is that the direction that the voltage increases is opposite to the direction of the electric field. So if the electric field is pointing to the right, then that means that the potential difference increases in this direction. Okay? Electric potential difference increases in the opposite direction of the electric field. So here in this case, we have a constant field to the right, so the electric potential difference must increase moving to the left. Okay, so the potential gets bigger to the left. All right, well, let's take a look now at another example with the same kind of setup here. The same kind of electric field here. So using this uniformly charged infinite sheet. So suppose we're a distance, let's say d, away. We're a little positive charge here, q. We're a distance d away from that plate. And we move to a distance d over 2 away from that plate. So now this distance is d over 2. Let me go ahead and just, delete that there. So we start at a distance d and we end up at a distance d over 2. So this is our point A and this is our point B here. So from A to B. What is the change? What is the change in electric potential given that this is our electric field That's the question, right? That's the question. So let's try to do it together here. Let's try to think through it together. So what are your guys' thoughts? Like what formula or what's the thought process here that we want to start with? So I'll let you guys kind of tell me, and then I'll do it up here. So we're trying to calculate delta V. We go from point A to point B. Simple as that. So point A to point B. What should we do? First of all, what's a relevant formula that we've developed that involves the electric field and the potential difference? I see there's a chat here. KQ over R, that would be a big mistake, right? Because we don't have a point charge electric field here. We have this electric field. We have a constant electric field due to a sheet of charge, right? Not a point charge. So we already know the electric field here. We don't need to use the point charge formula. So what's the relationship between delta V and E? Or rather, the vector E. Does anybody have any ideas? V equals Q times E. No, that is not a formula that I have ever written down. You're probably thinking of F equals Q times E, or delta U equals Q times delta V. So no, these are not going to help us, right? Certainly V does not equal QE. V equals E times delta X. Okay, I like where this one is going. I like where this one is going because it's a simple formula. It's a simple formula. V equals E times delta X. So I think what you mean is magnitude of E here. Okay. Okay, John, yes, yes. Good, I like this. Except del, you mean dx, right? You mean dx. Or what do you mean here? Oh, no, no. Okay, I get what you're saying. So you want to take dv by dx is equal to q times e, and you want to move the dx over. Is that what you're saying? qe dx. Yes, I like what I'm seeing here. I like what I'm seeing here. I like what I'm seeing. Anybody else have any input on that? Anybody else have an idea? Give me a thumbs up if you agree with what has been said so far with any of this. Just give me a thumbs up if you agree with any of this. Okay. So only maybe about half of you. So yes, this is the correct thinking here. Now, it is true that this formula right here will indeed work. Let's show why this formula actually works here, okay? Start with the fact that delta V is equal to minus, oh, by the way, there shouldn't be a Q here, John. There shouldn't be a Q here. I just realized that this is incorrect here. No Q. If you take the Q out, it's fine. But without the Q, only without the Q is it correct. Okay, so correct that. Everybody, if you wrote down with the Q, take that out, cross out that Q. So back to over here. So let's prove that this formula right here is actually a good formula. So the change in voltage here is the integral along some path of vector E dotted with some path element dr here. Well, we're moving along the x direction here, right? We're moving along the x direction. So let's come up with a path that goes from, say, d to d over 2. And our dr vector is going to be minus dx, x hat. And our electric field is sigma over epsilon naught x hat, right? This is just the plane, the sheet of charge, right? It's sigma over epsilon naught. If you want, you can follow along. You can substitute in just the capital E here instead of sigma over epsilon naught. But it is important here, it is very important that we know that that magnitude E is constant. So that's why I've written it down as sigma over epsilon naught, because we understand that that electric field sigma over epsilon naught is a constant electric field. That's very important here. Okay, so we've got now the dot product between x hat and x hat, and that's nice and easy, right? So integral from d to d over 2 of sigma over epsilon naught times dx with a minus sign, so the minus changes the sign outside to a plus. And we're integrating from d to d over 2, and there's no x here in our integrand, so this is a nice simple sigma over epsilon naught, which is the magnitude of E times delta x.
Okay. Maybe let's not write it as delta x, but basically it's delta x kind of confirming this formula over here. But we want to make sure we get the sign right here. So it's going to be x evaluated at d over 2 minus x evaluated at d. And so what we end up with is minus sigma over epsilon naught times d over 2 here. Okay. So do we have any questions about that? Oh, maybe we should check our answer now. Does our answer make sense, right? Does our answer make sense? So for our answer here, we know that we have to do work to push a positive charge against an electric field. So actually, our answer should be positive here. We should have a positive answer. So delta V should be positive because delta V increases in this direction. Delta V increases along this direction. So where did I make a sign mistake here? I keep making sign mistakes today for some reason. Oh, I know what I did. I know what I did here. So we should not write the integral from d to d over 2. That's a mistake. We should write because dx is measured this way. Dx is measured along the negative x direction here. We should start at 0 here and integrate to d over 2. Start at 0 and integrate to d over 2. Maybe, you know what, now that I'm thinking about it, maybe that was the mistake that I made all the way back at the beginning of the lecture. That could have been the mistake. I'll double check. I'll go back and look at it. That might have been the mistake, actually. So we go from 0 to d over 2 because d over 2 is the distance, is the displacement here, right? From our starting location. We go from d to d over 2. So that's like from 0 to d over 2. If we do that, then we actually get a positive sign here and it's all correct. So actually, let's make that change. Let us make that change now. 0 to d over 2, 0 to d over 2. So we do get a positive answer. That's good because our potential difference should increase as we move to the left. So sigma over epsilon naught d over 2. Boom, there it is. That's E, the magnitude of E, times delta x, right? The magnitude of E times delta x there. There it is. So that's a nice formula to use when you have a constant electric field. But in general, you want to use this integral expression here. In general, you want to use the integral expression. But for a constant electric field, we do have E times delta x. All right, any questions about that? Okay, no questions. So later we'll use this same result. We'll actually use this result here for an infinite sheet like, oh, you know what? Oh my God. Oh, I actually made another mistake here. There should be a 2 here. There should be a 2 here. This is the electric field when you have 2 sheets. When you have 2 sheets of charge of equal and opposite charge, then it's sigma over epsilon naught. There should be a 2 in the denominator here. Sorry for that. Making a lot of mistakes today for some reason. Sorry about that, guys. So fix that in the notes there so you have it correct. There should be a 2 in the denominator of the electric field. Sigma over 2 epsilon naught. Sigma over 2 epsilon naught for the electric field. So get that 2 in there so you have it correct in your notes. Sorry about that, guys. Yeah, so if you have 2 sheets of charge, if we were to add in a second sheet of charge here, like so with negative charge, then it would be sigma over epsilon naught. And that is what we're going to do in the future. We are going to look at cases where we have two infinite sheets of charge here, and we'll calculate potential difference between these 2 sheets. Okay, we already know what the answer is going to be because we just basically calculated it. And then we'll use that answer to determine some properties of a device which is built out of two sheets of charge there, namely a capacitor. So that's what's coming in the next chapter, which is going to be really important in the subsequent chapters as well. So I believe that covers. That covers everything here in this chapter. We didn't get to do too many examples, but we did get to do a little bit. Oftentimes, as we progress through the material here in this class, there's a lot of repetition of examples. So for example, in the textbook, they're going to show you, I'm going to clear this. Okay, can you guys just give me a thumbs up real quick if I can clear this? We're almost done. I'm just going to talk about some of the examples in the book. We're not even going to do them. I'm just going to talk about how they're very similar to what we've already seen. Okay, I think that was almost everyone. So I'm going to clear this. Okay, there's a recording anyways, right? So, okay, so in the book, they're going to take a look at a ring, and they're going to ask the question, what is the potential at this point here, right? You guys can already figure that out for yourselves, because you know now that V of R minus some constant, like some V0, is equal to minus that integral of E dot dr, right? So you already know how to figure them out. But what the book is going to do, I believe, is they use the standard integration technique, where they say, okay, there's a dq here, and so the potential at this point due to dq is k dq over r, and then they use that standard integration that we've been doing for a while now to figure out what the total potential is at this point p here, right? And so you'll see some examples like that. I already did mention in one of the previous lectures that the principle of superposition applies for potential difference. So we do have superposition here, except the difference now is that this guy's not a vector. So you just add these guys up as scalars. You just add them up as numbers. So they can be positive or they can be negative, but you don't have to worry about vector components. So the only thing that's relevant here is the distance between the charge and the point you're interested in. So actually these integrals are even easier than the integrals in the previous chapters. So so take a look at them. They should be super simple and straightforward, especially because we've already seen them with like the electric field and with the force, right? So they should be super simple there. As I go around the ring here, we can tell that the value R is going to be the same no matter what, right? No matter where I am on the ring, because we have the symmetry here. And so this integral here is going to be some integral over k, and then there's dq here, right? And dq is, if the radius here is a, right, then dq is going to be given by, something in terms of like dA and so forth. So take a look at those integrals. They're real simple. I'll just give you the answer here for the ring, just so you can see kind of what I mean by it's simple, because it really is fairly simple here. So the answer here for v of, and actually they write it as v of x here because they measure x along the x-axis here. So they give it in terms of x. They give the answer k. They actually write it as 1 over 4 pi epsilon naught, but we can write it as k. kq over square root of x squared plus a squared, where a is this radius right here of the ring. So it's a very simple expression there, right? It's basically just replace r with square root of x squared plus a squared, right? It's really that simple. So that's really nice that the electric potential is a scalar rather than a vector. So it makes these integrals a little bit simpler. So take a look at the examples in the book as always, as you're going through and reading the chapter and doing problems and homework and stuff, and use the book as a resource. Okay. Somebody mentioned that we should talk a little bit about the lab, the field of a permanent magnet. So I'm just curious, what are the questions for the lab?
I have one particular question. So
Okay,
in the video,
one second, because Jiho messaged me first in the chat here. So
right.
He said, how should our lab report look like? Well, I've gone over this several times now, so this is the very quick version. Intro, procedure, calculations, results, and conclusions. If you're asking me like kind of directly how your lab report should look, like literally if I look at your lab, how should it look? Well, you should have like a title, right? You should have your name. You should have like lab 1. That helps me sort it out in the grade book. You should have, okay, intro and then some text, right? Maybe an equation like B proportional to RP. For procedure, you should have some more text, right? You're kind of saying what you're going to do. Then calculations and results. Well, you should have some sort of calculation, 4 times 2 plus 3 all over, 7, right? Equals some number. And then on your next page, right, you should have a table with some data on it. Okay, and then your conclusion, right, is just more text. Okay, so that's what it should look like. As far as the procedure, just carefully follow what it says in the lab report. Let me tell you how many times students have gotten stuck in a lab because they think they know what's going on in the lab, and they just don't read the actual lab manual to know exactly what to do. And so they think they know what they're doing, and so they kind of make a little bit of progression, but then they get stuck because they didn't follow exactly what the lab manual was telling them to do. So read the lab manual carefully. It tells you exactly what to do for the lab. So if you're confused, read the lab manual, read it carefully. Okay. And then I think it was Duke, you had a question.
Yes. So I was watching Professor G's lab video, and one of his lab videos, he was explaining on the log and log plot, and then how like calculating error. So I was wondering if we include the error part of the calculation in there as well, or do we just stop at the log and log plot? Because on the manual that I read, it only says use the log and log plot just to predict your hypothesis. So
yeah, so for this first lab report, I don't think I'll be looking for some error propagation here. I just want to see that you guys do the lab appropriately, like get some decent data and get an answer for the p-value. What should we expect for the p-value? I think it's pretty obvious. Everything we do is kind of proportional to 1 over r squared, right? So we should expect p is approximately -2. That's what we should be looking for. So if you're getting like -3, -4, somewhere in that ballpark, maybe do it again and try and get better data.
it's because
yeah,
it's because the log and log plot that he showed, the calculation, like the slope, actually led us to a number p that's different than the one that we actually did it with our compass. So I was wondering, like, do we actually do the error, but
well, how did you calculate your p-value without doing the log?
So the first part he showed was like using the log which of R2 over R1, and then do the log of P. So that's what we did with the, that's what I did with the compass and the magnet. And then the second one he did was like putting it into a log and log plot and then finding the slope. And then he showed us like equivalently like that, the slope thing, and then with the log of B, it equals to like y equals mx plus b. And so that slope would be that value of P. But when I did it in my with my data, my raw data, the P came out to be different than the number that I calculated by hand.
So double check your calculation first, and then double check that you make sure that you're doing the log plot correctly.
Okay.
Because it's something that should, if you used your data to calculate P, right? I think if you look at the theory of a log plot, if it says the slope should be P, then it's essentially you're calculating P from the exact same data set. It should be the exact same value, right?
Yeah.
So there should be like a mistake in there or something if you're getting different values.
Okay, let me check. If not, then I just put it in the conclusion about what I got.
Yeah, you could. That's always like if you ever go through a lab and you feel like, okay, something's not working out, conclusion is the best place to put that.
Okay.
Yeah.
All right. Thank you so much.
Any other questions about that? I think we're done here today. We can end a little bit early because we've covered everything that we need to cover. But I'll be here to answer any questions you guys have. So if you don't have any questions, feel free. You can leave the call now. If you do have questions, you can stick around. Sean K, you said in the chat, like the line part to get the error of the slope. Yeah, you can do some sort of error analysis on this lab if you want to, but I won't really look for it too much. Yeah, lab should be in person this Thursday. Yes. Linest is an Excel function for reporting the best fit line parameters. Oh, okay. Yeah, so whatever if you use the trend line on your plot, or if you use some other function to give you the like equation, whatever you use is fine.
Professor, so the lab is due on Thursday midnight?
You can turn the lab in to me in person on Thursday.
Like using a flash memory?
Well, you can like bring and turn the lab into me on when we meet on Thursday, or yeah, you can like if you want, you can email it to me as well. But yeah, sometime on Thursday, just get me the lab before the end of Thursday. That's fine.
Thank you. Have a good day.
Okay, thank you, and yeah, you too. Okay, Sean, Juan, what do we got?
So our intro shouldn't actually like report, or like abstract shouldn't actually report our results. It should just be sort of like what we're studying, and
that is the difference. That is the difference between an abstract and an introduction. Is that in an abstract, it's a complete summary of the report, and usually an abstract comes before an introduction. So I usually require an introduction, not an abstract. So in an abstract, yeah, it's okay. You can report some of your results, but in an introduction, usually you just put the theory behind the lab. So I'm okay with that. If you want to do abstract for this first lab, that's fine. Want some water? Juan, do you have a question?
I remember you sent a video of Professor G explaining it. Was it in an email? Because I don't remember.
It's on Canvas.
Oh, it's on Canvas.
Go to Canvas, go to syllabus, the syllabus tab.
Yes.
And then click lab schedule, the lab schedule tab. And then there are hyperlinks there for each of the at-home labs. You can click and it'll take
Oh,
you to a video. Yeah.
And also for like calculations, how like do you want us to do like at least like 10 different calculations when we do the labs?
Nope.
Do you want us?
Nope. One calculation of each
I meant,
type.
but when we do it like at home, I know in the lab you want
Use
one, but
Excel. Just use Excel to do all of your calculations, right?
I mean, what do you call it?
Like, why would you want to write them all out by hand? That's going to take a long time, right? So don't do that. Just use Excel.
And how many like trials or whatever do you want us to do? Like around 10? Or
Yeah, you should try to do as many as you can, yeah, until you're just really not getting any data.
okay.
Right? Because
That's
if the magnetic field if the magnetic field gets too weak, then you can no longer trust your data anymore, right? So you have to make your spacing kind of small enough so that you can get a certain number of data points.
okay.
Try to get at least 8. Like at
least 8?
Yeah.
Okay. That's what I meant. I didn't mean calculations. I meant like trials.
Oh, okay, yeah.
Yeah,
Or
I just
data points.
Data points, yeah.
Yeah.
I blinked out.
Okay.
Right.
Yeah,
Right.
so that should be fine. But yeah, don't waste time doing all your calculations by hand. Just use Excel.
Right.
Any other questions, guys?
That's it. Have a good day.
You too. All right, Sean, I'm going to end the call if you don't have anything for me. Okay, have a good day.